All right. Good morning or afternoon or wherever you are to everybody. I am not Katie Felkner, who is the host of language seminar. She is ill today. I'm Jonathan May, and I'm happy to introduce our first speaker of the semester, who is Lee Kezar. Lee Kezar is a fifth-year PhD candidate in the USC Viterbi School of Engineering, advised by Jesse Thomason in the Grounding Language and Actions Multimodal Observations and Robotics Lab, or GLAMOR, one of the many nicely named labs in USC's computer science department. Also shout out to the Dill Lab and of course QLab. Anyway, their research blends computational linguistic and psychological models, ASL, to increase access to language technologies and advance theoretical perspectives on signing and co-speech gesture. This is Lee's bio that I was provided, but I also wanted to say on a personal note, Lee was in I first got to know Lee because they were in my first CS 662 Advanced Natural Language Processing course in 2019, and were a font of really interesting debate. I'm really glad to have seen their progress through the years as they work on this very challenging problem in the NLP and machine learning space. I also want to acknowledge Rigoberto, who is providing ASL interpretation, including everything I say. Monsters are coming to attack my grapefruit. Nice. Anyway, so thank you, and thank you to ISI for sponsoring the interpretation as well as this entire seminar. Also, on a programming note, I want, for those of you who are in the Los Angeles area, I'm also part of the Center for Computational Language Sciences, CCLS, and there will be an upcoming talk next week on Wednesday. Roger Levy, professor at MIT, will be coming to speak. You can register for that and for lunch at tinyurl.com/CCLS registration, all one lowercase word. All right. Notes out of the way, it is my great pleasure to now let Lee take over and tell us about their great research.
Thank you. Like John said, my name is Lee Kezar. I'm a fifth-year PhD student in computer science. And this is research that I basically entered USC wanting to do. And it has been challenging, especially as we have not had a lot of data to work on this task. But over the years, it's gotten more interesting and more fun as we go along. I put this, this is from the Starbucks across the street. I went there this morning and they have ASL letters, sort of the manual alphabet spelling welcome on the chalkboard. I thought that was definitely topical. I did not expect to see that. So when we think about how natural language processing could include sign languages, there are many applications that come to mind. For example, linguists might be interested in automatically transcribing things like phonological features and signs from video data. You can imagine how tedious that is to do manually. We can also think about, for example, Duolingo provides spoken language feedback as you're learning a language. There's no such thing for sign languages at the moment. Search engines could be useful for finding particular content in a long video, for example, like 20 minutes. You can imagine you'd have to watch the whole 20 minutes in order to find something as videos are currently processed. Similarly, we could summarize that content. We can think about what it would mean for ChatGPT or Alexa or Siri to include signing as well. And of course, everyone sort of thinks about translation with sign languages, either from a sign language to a spoken language or to a written language or to another sign language, for example. And as we think about including sign languages in NLP, I think it's topical to also say that we should include deaf people in sign languages. By pure coincidence, this week is the International Week of Deaf People. Monday was the International Day of Sign Languages, which is also fun. The one thing I will say about the cultural side of this technology is that it's important to understand that this is a socio-technical system that we're talking about, any of these applications. And so there are tensions that could exist between the technology and what it's doing and deaf people and what they want. And it's sort of useful or fruitful to think about that tension in the technology. If you wanted a good book to read, this one's short. I think it's about 100 pages. And it sort of addresses how technologists and computer scientists are definitely among the most guilty tend to think of technology as something that is helping a disabled person, when instead, we should be asking, for example, how do we empower people with disabilities? So in this presentation, I'm going to introduce sign languages and NLP. I want to give some background on how we think about form and meaning in the ASL lexicon. And then I'm going to introduce a framework called Linguistic Knowledge Infusion. And it's divided into 3 different sort of sets of methods: shallow, semi-deep, and deep knowledge infusion. And I'm going to pause between each of these sections if you have clarification questions. And then there's also 15 minutes at the end for discussion. Please interrupt me, though, if you have a burning question that can't wait 10 minutes. Let's get started. So as a way of introducing this intersection, I've shown here the histogram of papers published in conferences with sign language in the title. And as you can see, work has been sort of continuous ever since 2000, but in the last 5 years, it's sort of taken off in a new way. Of course, even at its peak, 53 papers compared to the NLP papers for speech and text is nothing. There's probably tens of thousands of papers published every year that are about speech and text, but nonetheless, it's promising to see this increase over time. Hopefully it continues. And then among the titles that I found, I did a pretty simple trigram analysis of the words in the titles. And so we can see some of the common words that come before sign language and some of the common words that come after sign language in the titles of these papers, just as a way of characterizing the field. As you can see on the left, there's a number of specific sign languages that these papers tend to focus on. For example, German Sign Language or Indian Sign Language. There's also a couple of tasks that are in here as well. For example, continuous sign language recognition, which is given like sentence level data. And then there's also isolated sign language recognition, which is just individual signs. So these are the topics that we'll be talking about today. I primarily focus on American Sign Language, although some of the methods, it doesn't need to be ASL, it could be any sign language. Most of the talk is about recognition, recognizing signs, but towards the end, I want to talk about understanding signs and sort of our early work on that as well. So what is isolated sign recognition? It's easy to define. We have a video, it's usually a few seconds long, and it's someone producing one sign. And the goal is to identify what the sign is. Very simple. Two data sets that have been introduced for this task, and there aren't many, these are sort of the most used in the field, is word level ASL and pop sign. Word level ASL is sort of scraped from YouTube, and it contains about 20,000 videos representing a vocabulary of about 2,000 signs. And that produces an average of about 10 videos per sign. On the other hand, pop sign is substantially larger, about 8 times larger than word level ASL. These videos are hand curated, so we absolutely know what the content is in each video. And a much smaller vocabulary, 250 signs. Pop sign was meant to be a game that parents could play to learn ASL. You can imagine that because over 90% of deaf children are born to hearing parents, there's a sort of vacuum that's created where parents don't really know a sign language, and that's the primary language that children deserve, deaf children deserve. Yeah, John.
So I have a question which is about the relationship between like the notion of what a word is, the notion of what a sign is, and then like a lemma versus a conjugated word or a word, and what you mean over there. I'm wondering if this is the right time to ask that question.
It is. Okay. That's a good question.
Presumably you can understand the substance of my question.
Yeah.
Explicitly asking it, so.
Yeah. So the question was, what's the difference between a sign and a word, or in linguistics, we might call it a lemma. In these cases, the sign is more like a lemma in the sense that it has not been modified to include any kind of morphology. For example, you could say 1 day or 2 days, and the difference between those two signs is your handshake. But we might call those just day in the lexicon, but it could be modified to, you know, reflect number. Or another example is like give, just as a word, and then give to me versus he gives her. Like all of these things show directionality, and those are not usually included in these data sets. So
I would, you know, was not talking about sign, would never even think of those as being alternates. I would just talk about give versus gave. Oh. Which I can't even tell.
There's tense as well.
Yeah.
Yeah. So
just that, and not he gives to her as a sentence, as far as I can tell.
Yeah. Yeah. And in ASL, that could just be one sign. So like, you know, you give me, or like Justin gives me, you know, or you give Justin, you know, the directionality kind of matters.
So a sign really here, you're kind of meaning a sentence then?
No, the translation could be, you know, a predicate, but it's kind of rare to, I mean, you know, in Spanish, we could say like dímelo, like that's one word, but, you know, whether that's a sentence is sort of, you know, kind of rare. Okay. Looking at some of the models that have been produced for sign recognition, isolated sign recognition. I should start by saying technically these two things should not be on the same graph because these are two very different tasks. Recognizing one of 2,000 possible signs is very challenging compared to recognizing one of 250 signs. But the performance for word level ASL kind of plateaus here. You know, why that is probably related to the fact that there's not a lot of, you know, there's not a lot of examples for video. But for pop sign, this was formatted as a Kaggle competition, and they awarded like $100,000 to the winner of this challenge. So substantially more dots in this area in a short period of time, but the maximum that they were able to achieve is about 90% accuracy. And what I want to point out in sort of this, it's great that we're able to get 90% accuracy on this task, even though the vocabulary is not really usable. It's more for educational purposes. And likewise for word level ASL, 2000 is hard, but still unusable. The actual vocabulary could be, you know, in the tens or 20 of thousands. My hypothesis is that we're treating this task like generic gesture recognition, where we are given examples of the sign and we know the label, but that's about it. We don't have any extra information about what the signs are, what they look like, what they mean. And so we are asking the model to learn this representation that goes from a really highly dense format of video to a specific ID or class. So it's pretty challenging, but there's more information that we can include about signs, and a lot of that information comes from linguistics, sign language linguistics in particular. So I'm going to show a few examples of signs to illustrate some of the properties that we can think about. So on the left is the sign for vote, in the middle, president, and then on the right, the name sign for Kamala Harris. I'm going to describe why this sign is her name sign in a moment. It's a really cool story. We can think about the phonological descriptors of these signs. For example, how do the hands move? Where are the hands located? And what configuration are the fingers, otherwise known as a hand shape?
I can't tell which direction each of these signs is going.
Yeah. If you're left-handed, then it's going to look different than if you're right-handed.
Is vote this in or out?
Yeah. Vote is going to go like in the hand.
And president?
Unless you're stealing votes from a ballot box, in which case you remove it.
And president? Out or in?
It starts at this and then ends with this. Yeah, from this side. Yeah. Kamala is sort of this sort of motion. Can also describe some of the more fun. Oh, there was a question in the back.
Yeah, sorry. So for names, I'm guessing because like Kamala is very popular figure, so only like one letter, one sign. But usually for names, like this is a combination of letters or like signs, or it's like one gesture.
Yeah, name signs usually are sort of like an abbreviation of a fingerspelled version in English. And so, yeah, not everyone has a name sign, of course. And so this is sort of like a unique case. But there are many sort of famous name signs that are beyond my skill set. Yeah, so these are some of the ways, we use a data set called ASL-Lex. This contains 16 different types of phonemes for each sign. And these are just 6 of the examples. There's several more. And we can also sort of begin to think about what are the semantic features of these signs. And as a way of introducing the semantic sort of nature of signs, we can think about signs as having an iconic relationship with meaning, meaning that the sign kind of shows what the sign means. Or it could be arbitrary. I'm pretty sure that president is arbitrary. I can't think of a way that could be iconic, but big hat. And then just to give you a little background on Kamala's name sign, it sort of initially was created by a group of deaf women who are Black and Indian. And collectively, they sort of studied her name and what it means, and as well as who Kamala is as a person. And they came up with this representation, or this sign, which is related to the sign for lotus, which is what Kamala's name means. And the 3 comes from her position as the first woman, first Black person, and the first Indian to hold a position in the White House, or sorry, in the vice presidency. So the 3 sort of firsts that Kamala sort of represents. I wonder if it'll change to 4 if she becomes president. Oh, we'll see.
She wouldn't be the first Black person that, so.
Yeah. 3.5. I don't know. And so we recognize that we have all of this information about signs and sort of organized it into a benchmark or a data set. The core of the data set is these labels for signs, video examples, and in the SEMLEX benchmark, we have 91,000 videos for vocabulary of about 3,000 signs. And we also have an English translation for the signs as well. And just as a point of detail, this is a many-to-many relationship, not one-to-one. So there's a little bit of complexity there, but I'm not going to go too deeply into it. We also have phoneme labels, like I mentioned, at least 16 per sign. And we also collected semantic associations. So for example, cat might be related to dog. We got these directly from deaf participants who we paid. And so it's sort of like within ASL, it's not really using another language. We also have semantic relationships for English words that come from classic toolkits like WordNet. And we have semantic labels as well. For example, a word might be related to vehicles or related to food. We hypothesize that these kinds of features will be helpful in mapping the relationship between form and meaning. For example, male signs are usually produced on the forehead. Female signs are usually produced near the chin. So, gender might be one of these semantic features that we might think about. And we, recognizing that this is a lot of different types of information and they have sort of complicated relationships with one another, a knowledge graph is sort of the ideal form to capture this information. You could also, I guess, use a table of sorts, but it would sort of underrepresent the sort of more complicated relationships that are going on here. And I want to give a shout out to KGTK, the knowledge graph toolkit that we use to build this. This comes from ISI, the Center of Knowledge Graphs. We have the representative from the center here. Be sure to forward all of your questions to him. I'm just kidding. To give you a sense of the size and breadth of this knowledge graph, I've shown just a few, random pieces of information. On the left, we can see the different sources of information. There's at least 7 different sources that we're using here. And in this table, I've shown kind of the layers of the linguistic stack that are represented at varying degrees. For example, there's a lot of information. This number is the number of facts or the number of triples that are in this category. The phonological features and semantic features are some of the biggest, as well as translation. There's also some information about for example, morphological features like the number of morphemes, but this sort of represents sort of what's available in the field currently. Any questions at this point? Yeah.
First of all, it's all super, super cool. Just how many, you were talking before about like unique signs or like hand gestures. In this case, which variable is representing them?
Yeah, in the knowledge graph, many of the facts are represented as sign, has property, value. And so we can think about, for example, cat has hand shape F, but also cat is related to dog, and cat is a type of animal, et cetera, et cetera. But that's sort of the bulk of the information. And there's also some like connections that connects, for example, English words to English words. And it kind of gets messy, so it's hard to wrap your head around, but yeah. Does that answer your question?
Yeah.
Okay, Jay.
So a lot of the data is video. So are you trying to, is there like a relation type for like, here's where the video file is located, or how does that work?
Yeah, currently the video examples are not sort of explicitly in the knowledge graph, although we use common labels to make sure that you can sort of map them back and forth pretty easily. But yeah, right now they're separated. Yeah.
Are the videos like static or dynamic movement and gestures?
All of them are, include time as a variable. Many signs use some kind of movement. There's a very small number that don't really have a movement, but even in those cases, we still use video just because it's easier to keep it consistent instead of having a totally separate model for like, for example, like one letter, which is not going to really appear that often.
Could you clarify again how you got, you might have already said this and I missed it, how you got each of these like links?
Mm-hmm. Yeah, so a lot of these data sets have a similar kind of structure where the rows represent signs and then the columns represent features of those signs. There was some trickiness about, whether it's appropriate to combine certain signs just because they have the same name. That's kind of like an English-oriented way of merging signs, so it's not ideal. I primarily use phonological features to help merge the signs, treating those like evidence. So for example, data set A may have a sign for computer and it's using the C hand shape, but another data set may have a sign for computer, but it uses the open 8 hand shape. And those signs are like computer versus computer. So we wouldn't want to combine those two things. Those are different signs. That have subtly different meanings. For example, like older people tend to use this version because it represents like tapes moving in a computer, whereas this one is used by more like, more recent cases. But yeah, we're sort of combining the information.
So there were like several other data sets that were already taken this information.
Yeah. Mm-hmm. Yeah, we're taking linguistic knowledge that other experts have sort of collected for us, and we're bringing it all together into one sort of big data structure. I should cite all of these. I apologize for not doing that. Lancaster, just to point out a couple of these, Lancaster sensory motor norms is information like taste and smell and sight, like how whether words are aligned with those sort of senses. Lucan Empath contains features like related to vehicles or related to being female or something like that. Okay. So for the task of sign recognition, and we're going to kind of bounce around a couple of tasks, but this is sort of the main one. Once again, we have a video input, sign output, and it's unsurprisingly, we use a lot of encoder decoder kind of models. The encoder's job is to sort of represent the video in a way that a decoder can sort of classify the sign. We use something called an SL GCN for the video encoder. This is a graph-based network, and so we use pose estimations instead of video. If you think about it, there's really not a lot of information in video that we need that isn't found in pose, and video introduces the possibility of spurious correlations with race or other identifying factors for the signers, and we kind of want to avoid that. Yeah.
Does facial expression or pronunciation come into play, and is that covered by pose?
Yes and yes. Facial expression is used as a phonological feature. Yes, the pose estimations we use include the face. And the way that we can think about improving this setup, which is kind of like an end-to-end setup, is by infusing the linguistic knowledge that we collected into the ASL knowledge graph into the parameters of the model. And the Chef et al. Sort of created this framework called knowledge-infused learning, where you infuse the knowledge of, or for example, a knowledge graph into the parameters of the model at varying levels of depth. So there is shallow knowledge infusion, semi-deep, and deep. I'm going to give definitions of these as we go, but the general idea is that we want to take the ASL knowledge graph and then use that information to help shape the parameters of the model itself, or the way it learns. So starting with shallow, the definition that they provide is that it contextualizes training examples with expert knowledge. This is not a new phenomenon. We have been using expert labels for language for a really long time, probably ever since NLP was a field. And in this case, what kind of information could we include? We can sort of think about including an auxiliary loss, which is a really simple way of contextualizing training examples. We say that in addition to predicting the sign, we might also want to predict what the hand shape is or where the hand is located. And in doing so, the model is sort of forced to attend to certain phonological features that we know are going to be important for recognizing a sign. In doing so, we see significant gains in accuracy. This paper was done last year on the word level ASL data set. We see an improvement of 8.7% overall. And because word level ASL does not include phonological features on its own, we had to like sort of add them by looking at aligning them based on gloss with ASLX. Many of the signs we couldn't align, and so there's about half of the data set is labeled with phonemes, and then half the data set is not labeled with phonemes. And these are on a sign level basis. So there's not going to be like one example of cat that has the F hand shape and then one that does not. Like either we have it or we don't for each sign. And as you might suspect, the videos and the signs that do have phonological labels, the improvement is even more. But what I find really interesting is that the signs where we did not know what the phonemes were, the model was able to remember those more accurately as well. So the process of learning how to identify hand shape is not only useful for the ones that are labeled, it's also useful for all signs. And we see a similar phenomenon for an off-the-shelf transformer model. It didn't do as well, but the increases are sort of across the board. And using the SEMLEX data, which you might remember is 90,000 videos, we get an accuracy of 66%, which is a little bit better than the state of the art for word level ASL. The auxiliary loss contributes 3% of those accuracy, 3 points to that accuracy. And we specifically studied signs that were rare in the data set. So, sort of the long tail of signs that don't have many examples. We see that the model recognizes those even more accurately, sort of disproportionately more accurately. And it's a small difference, but we also attempted to measure the sensitivity to race, gender, and age by developing the test set such that these groups are sort of overrepresented, whereas in the training data, these groups are sort of underrepresented. And so the difference between validation and test performance is about 1%. And it's, whether that's within the margin of error is debatable, but, still important to sort of measure explicitly. Another way of approaching shallow knowledge infusion is to think about phonemes as characters in a word. It seems like using them as an auxiliary loss is not really taking full advantage of the fact that there's a pretty clear statistical relationship between phonemes, the parts of words, and words. And so we can come up with graphical models that map phonemes to the sign. For example, we can train the video encoder to produce predictions for the 16 different phoneme types, and then map those phoneme types to a sign using, for example, a factor graph model or a nearest neighbor model. These are obviously much more lightweight than using a decoder model and much more interpretable as well. If it helps, you can also think of this like spell correction or spell check, because the video that's predicting these phoneme labels is always going to be a little bit wrong. In fact, the next slide I have the accuracies across the 16 phoneme types, and I could describe these in detail if you want, but for sake of time, I'm just going to sort of loosely call them location, movement, and hand shape. The accuracies for the model are between 75 and 95% accuracy, so reasonably okay. And in blue, we see the majority class classifier performance because these are imbalanced classes.
Wait, so majority class given what?
There's no input. It just always picks the most common phoneme for this particular type.
Right, but then all the blue sum to one. No,
No.
not even.
No, these are all independent. These are
Oh,
independent
this
variables.
is a binary classifier per sign.
No, the input is a video. The output is the phonological features. This is 16 different classification problems.
Dimensions, right? 16
Yeah.
Dimensions.
And these are sort of there's a relationship between them, but for the most part, they're independent of each other. So there's no reason why they would sum to one.
So, okay, we can see majority class classifier. So let's consider HS left. In the HS left phoneme type, what are the classes?
So there's 50 possible, or about 50 possible hand shapes for either hand.
For the left hand, I see.
Yeah. Yeah. So input, video pose, output, the 16 phoneme types. And then going from the phoneme types to the sign, we have a vocabulary here of 2,700. This comes from ASLX. The factor graph model gets about 48% accuracy. And here the factors are assuming that variables that are related to location are going to be conditionally independent of the variables related to movement and hand shape, just for the purpose of making this tractable and computable. You can imagine that among the hundreds of phonemes that are represented in these combinations, it's not possible to compute the probability directly. So we have to use a factor graph model. Compare that to the auxiliary loss, which does substantially better. But then the result that really gets me excited, because this is a huge improvement over the state of the art, is the nearest neighbor model, extremely simple model that gets 81% accuracy at sign recognition. And here the definition between two signs, or two sets of phonemes in this case, is just going to be related to the overlap of those two signs. So pretty intuitive definition there.
The overlap of the feature values?
Yeah. Yeah. And if we decide that we want to use feature learning and perhaps train a small model for this task, we can use a multi-layer perceptron or MLP, and that gets 85% accuracy, so a little bit more. But this is really exciting because this is the most usable thing that's ever come out of sign recognition as a task, and we're going to be using this model later in the presentation.
So there's no soft. Sorry, like asking you.
Okay, go for it.
There's no notion, of course, of soft overlap here, right? Because like either you're getting it right or you're not. And like if we had gazillion signs, we could build some completely our own model. But the point is, you just really can't do that. You're not going to get anything this way.
Yeah, and also it's important for me, at least, that the model is interpretable in some way. So, a nearest neighbor model is attractive for that reason. But yeah, and this, by the way, this MLP was 2 layers, so not very large. Yeah, Jim.
So you said 16. I guess these are the 16 phonemes. What coverage do they have, or the phonemes used in signs?
Yeah, that's actually a really good question. I'm actually going to punt that until the end because I come back to this question. But the quick answer is there is a rich debate in linguistics, sign language linguistics, about what the phonemes are. You have many muscles on your body, and those muscles can be, activated in combination with each other in all sorts of different ways. And, the best way to map that to discrete units is not very clear. In speech, this is like the manner and the place of articulation. There's pretty stable relationships there, because linguistics has preferred spoken language for decades. If the same amount of effort had gone into sign language, you would probably have a better model. But yeah, this includes, I would say, the majority of features as people think about phonemes, but there's definitely some gaps. For example, facial recognition. Facial expressions are not included in ASLX. Moving to the next sort of layer of knowledge infusion, semi-deep knowledge infusion seeks to embed expert knowledge into the parameters of the model more directly. And one way of doing that is by knowledge graph node embeddings. And if you're not familiar with node embeddings, these are vectors that are associated with each node in the knowledge graph. So a sign or a word in English, or maybe the phonological features for those things. Each one gets a vector, and the way that we create that vector is by training a model to produce a score for each triple, head, relation, tail. So again, just to give you an example, like cat has hand shape F. We might, we train a model to produce a score such that real triples receive a higher score than triples that do not exist in the knowledge graph. So this is kind of like a discriminative model. There's many other algorithms for learning a node embedding here, but we found that Dismal does the best. And so in this case, we still are predicting the phonological features for each sign, but we also assume that there's more information inherent to these phonological features than just being, some random ID, for example, represented as vectors. We were hoping that this would improve the recognition performance. And we see that as the number of incorrectly recognized phonemes increases, that is, the mutation level sort of increases. Using these embeddings as the representation of phonemes does seem to help a little bit. These are the predictions on the train set, and black, it's kind of difficult to see, but the black line here is randomly initialized embeddings. And so the way that I interpret this finding is to say that the embeddings have a degree of error correction that are sort of like built into them. They capture some mutual information such that if you didn't correctly recognize, for example, the location, then maybe knowing the hands sort of helps you, the hand shape sort of helps you recover from that mistake. But in terms of sign recognition accuracy, it's sort of mixed results. The performance is 69%, which does not do better than the nearest neighbor model or the MLP, but still it's interesting. And we did find a more useful application for this. Excuse me, this is supposed to appear after. Oh, you know what? It's supposed to disinfection. Oh, that's fine. Oh, okay. Yeah, this is what I meant to say. We can predict the semantic features of signs directly from the phonemes. We go to the slide here. So if you recall from the knowledge graph, signs have phonological labels, but signs also have English translations, and those English translations have several semantic features. We're using these labels because it's sort of a closed set of possible semantic features. And this is the performance when you try to predict either phonemes to semantic labels or the other direction. And we compare just using no embeddings or a multi-hot representation of the phonemes versus using the embedded form. And we can see that The F1 does increase for using dismal. And what this is saying is that, I mean, first of all, this task shouldn't be possible. In spoken language, we have onomatopoeias, for example, and so there's that level of iconicity where the form of a word might tell you what the word means. And there's also, for example, TION can mean related to, like the word is related to a noun. There's sort of those relationships that exist in non-signed languages, but somewhat surprising to me that we get about 0.09 F1 for predicting the semantic features. And I put this on the wrong slide, but these are the semantic features in their relative performance at recognizing them. So I think of this as like a semantic back off. If we're looking at a sign and we've never seen it before, or we're not sure what it is, we can imagine using a semantic back off model to say, well, I think that the word is related to music, or I think that the word is related to family. And we might be able to use this information to decide where translation might be more suitable versus, other areas. If a model is able to recover from out of vocabulary signs in the musical domain, then maybe we would prefer it in that setting.
Is character recognition generally a thing like in the Connell case? If you haven't seen that name set before and somebody's doing a thing, presumably a signer would say like, okay, clearly that's got to be the name sign, and maybe I don't even know what you're talking about, and then after some details comes like, oh, that's
and there are many cases where signers are able to sort of understand intuitively through compositionality. They're able to understand what a sign means, even though they've never seen it before. Let's go on to the next form of semi-deep infusion. They also say that semi-deep infusion can be a method which guides the model's learning process. And we published a paper on this topic, and we explored, in that paper, we explored curriculum learning, where we think of the 16 different phoneme types as sequential tasks, and sequence them one after another in such a way that prior knowledge is helping you with the current sort of phoneme type. For example, it makes sense to first have the model focus on the location of the hands, and then predict the movement, and then predict the hand shape, instead of just thinking of these as like just one sort of 16 tuple that we should predict all at once. And we did find that this improved the performance on recognizing each of the phoneme types, but only by a small margin. I would not say that this is sort of worth repeating, but perhaps interesting to see that it does do slightly better than multitask learning, and it does better than slightly better than just learning the model for each phoneme type one at a time, and not having any overlap at all. So in this column we have 16 different models. In these we just have one model. And the performance is not evenly distributed either. Like the gain is not evenly distributed. For example, some of these phoneme types only improve by a little bit, and then others, for example, path movement, which is a difficult phoneme type to recognize, improves by about 4%. So, And then finally, moving on to deep knowledge infusion, we have a couple more involved cases. I'm going to try to go through them somewhat quickly, but the goal of deep knowledge infusion is to provide varying levels of abstraction throughout the model. And to be honest with you, this feels more like an art than a science. The original authors do kind of give some examples from the past decades in NLP, but whether, we could debate whether this is deep knowledge infusion or not. At any rate, one of the problems that has come up a couple of times with regard to accent and dialect, as well as the coverage of phonemes in the lexicon, one of the problems that comes up is that we don't really have a exhaustive way of representing signs. And the degree to which these phonological features map to signs is sort of lacking. For example, facial expression is a variable that makes a difference. For example, understand versus don't understand. The only difference between those two signs is the movement of the head. And so we'd like to include those. But of course, finding phonological labels for all these things and then getting experts to annotate 90,000 videos is not easy. So vector quantization is a unsupervised machine learning method where the input and the output are the same. We want to sort of compress the input and then use that compression to reconstruct the sign. And we specified that the encoding is two-dimensional, first of all, and in vector quantization, we separate that two-dimensional vector into several rows. And then each of those rows we can think of as a point in the embedding space. We say that this is quantized or discrete because we map each of these points to the nearest neighbor in some codebook. And the codebook is supposed to represent stable, coherent features that sort of exist across the whole lexicon, as opposed to being something that's like specifically for this input. And the argument that we present in this paper, which is going to be presented in the theoretical issues in sign language research, is that this sort of framing and these constraints that we put on the autoencoder are very phonological in nature. For example, we know that phonemes are discrete. We know that they are simultaneous, meaning that, for example, your hand shape has a particular configuration while it also has a location, and then it may move in that location as well. If we're modeling phonemes, we need to capture that relationship as well. In speech, it's strictly simultaneous. It's sequential. It's also descriptive because the codes need to be able to reconstruct the sign as opposed to, maybe satisfying some linguistic oriented model. In this case, we just want to describe the signs. And there's a number of variables, hyperparameters, that we can sort of manipulate here. For example, how many codes are produced for each input. In this visualization, it would be 3, but you can imagine if we require 10 codes for each input, those codes are probably going to represent something a little bit more fine-grained. And then if this is actually a somewhat popular method. Some people have used like 1,000 codes for each input. In that case, I would not go as far as to call those phonemes. It seems like they're just capturing like very small details that are probably closer to phonetics. And perhaps that's interesting for the sake of measuring accent or, these differences that are sort of within the same phonological description, but maybe the signing space is a little bit larger or the location has been dropped just a little bit. And those differences do reflect sort of dialectical differences. On the left, I've shown what the reconstructions for these signs look like. On top, we see the sign for new. On the left is the original. On the right is the reconstructed. And then the sign for protest as well. Is a little bit difficult to interpret these scatter plots, but we also attempted to predict the sign's phonological features from the codes. And this is sort of a weird experiment, but very cool. Without giving the model any kind of supervision as when it comes to like what the phonemes are. It was still able to come up with codes that vaguely look like phonological features. So this model is sort of coming up with its own computational theory of sign language phonology. And we're sort of seeing that it, by sort of, I don't want to say by accident, but without intention, those codes end up looking like phonemes. I'm going to quickly go through YouTube ASL because we're running low on time. This is the final sort of application, and it's more a pipeline, but YouTube ASL is a collection of long videos on YouTube and 11,000 videos to be specific. And all of them are in ASL, of course. And we have English translations represented as closed captions. We come up with this task of predicting the topic for each video using a very simple LDA topic model to produce a topic for each video. That comes from the English. And the goal is that we want to take the video as input and then try to recognize what the topic is. So this is where everything kind of comes together. We apply We call it a phonologizer, the model that recognizes phonological features from the video. We apply that to the video using a sliding window. From there, we want to recognize the signs. And this is just for clarification. I'm not going to read the notation out loud, but if you're curious, V stands for video, P stands for phonemes, little s is a single sign, and then the capital S is sort of the sequence of signs for the entire video. From there, we want to develop a way of embedding each of those signs, and for that we use BERT. We use English translations as a way of creating this embedding. And so each sign maps to multiple words in English. We embed the sign as a weighted average of those words, and they're weighted by ASL frequency. So, you know, a sign, for example, like luck is could also mean preference or taste. And so if one is more frequent than the other, we'll sort of weight that appropriately. And then the final embedding for the entire sequence for the entire video is just going to be BERT on the individual sort of embeddings. We split this data into 5 folds and then learn an MLP to map the video embedding to the topic. And this does about 8% more accurate than the majority class classifier. I think that this is a pretty challenging problem, so I'm happy with the 8% improvement, although there's definitely a lot more sort of room for improvement here. And so just to conclude,
so
oh yeah,
on the previous slide, I mean, for example, the factor graph model wasn't like the best
oh
one.
yeah,
So it seems like you could sub in the parts that you know work better and like
yeah,
potentially do better. I don't know.
absolutely. Yeah, this is ongoing work. I should have said we are actually I already have the nearest neighbor predictions. I just need to continue. The pipeline has gotten clogged and it's a work in progress, as well as the MLP on the embeddings. That should be part of it as well. We're hoping to submit this to NACL, so wish me luck. But just to sort of conclude, we introduced the American Sign Language Knowledge Graph. And I sort of characterize this graph as, yes, it's linguistic knowledge, but it's specifically related to form and meaning. And there's this sort of relationship that we've seen throughout a lot of the examples. And I think that relationship should be very helpful for understanding these videos. In the category of shallow, we showed that auxiliary loss and the phoneme to sign approach improve sign recognition accuracy. In the semi-deep, we showed that curriculum and node embeddings could be useful for adding extra robustness to these models. And then in the sort of deep knowledge infusion, we're able to sort of not only apply it to something that could be useful for downstream users, we're also able to sort of think about theories of phonology. For example, the question of how many phonemes are there is a really difficult question to answer. Perhaps, you know, we use the vector quantized model and we say that, okay, continue adding codes until you no longer improve the reconstruction accuracy. At that point, we could say that we fully described or sufficiently described the language. So that's all that I had prepared for you, and I'm happy to take any remaining questions.
Yeah, are there any questions on?
Yeah, I've got one. So,
hi.
So this was a great talk, Lee, and I'm really sorry I wasn't able to be there in person because I really enjoyed it. I wanted to ask, you mentioned at the very beginning of the talk about like ASL using chatbots or like virtual assistants, and I wanted to ask a little bit about the state of like ASL generation and what technological advances, research advances you think we need to make before we get there, and also like, what do you think those assistants would look like? Would they just be like a floating pair of hands? Would it be some sort of avatar or character? And then like, how do you think researchers and product development teams need to like be centering the deaf community while they're developing these kinds of products?
Yeah, that's a good question. So the first part was, where are we at with sign generation? What does the form factor for those models kind of look like? And how is the deaf community kind of treated in this process? So going from a video of someone signing to sort of like a understanding based output, whether that's recognition or topics, that's sort of one direction that we could sort of go in. We could also think about, for example, English to ASL that requires producing an avatar of someone signing, because that toolkit is just completely different from the toolkit that I'm using here. I decided to just kind of like focus on one side of this, although it is fair to point out there's sort of another half of this whole subdomain that needs to be attended to. My argument is that linguistic knowledge infusion is helpful for both of these directions. As we saw with the vector quantized model, we are able to sort of produce these sort of reconstructed signs. And that's sort of, I think of that as kind of like being at the center. We just want a good representation of signing, whether we're producing the sign or just looking at the sign. You're absolutely right that the deaf community should be centered in this work, especially, for something like the language learning app. There's so many hearing people who learn maybe 10 signs and then immediately go to YouTube and then try to teach other people those signs. And they're producing things in all sorts of weird ways that are not standard. And the problem is actually very serious. It sounds like some little side problem, but there's way more hearing people that are trying to teach sign language than there are deaf people who are trying to teach sign language. So, if we were to go in the direction of a language learning app, I personally will not work on that. I think that a deaf person should work on that, but I'm happy to help as necessary. For example, recognizing phonological features is a good form of feedback. I would argue, like if your hand shape is wrong, then the model could easily tell you, oh, you didn't use the right hand shape. But I'm not really in a position to prescribe what is correct and what's not correct. So I do want to be kind of careful about that. Good question, Katie. Yeah.
So you had this interesting finding where you said, oh, well, we didn't expect phonological semantic links. We have some semantic links in etymology, in like non-sign languages. This seems like a perhaps orthogonal evolutionary kind of track of meaning. So what, I guess, perhaps this is not a fair question, but do you think you have understood language better using this orthogonal understanding of semantics? And if so, what are the interesting kind of findings of how semantics work in language?
Yeah. A good example of how semantic sort of compositional knowledge could be helpful is with classifier predicates. So this is a particular type of construction in many sign languages, but I'm most familiar with ASL. For example, if you're describing a car accident, you'll use the three-hand shape to sort of symbolically represent a car. And the way that the hands move, sort of the plane of movement, or whether the angle of the hands, all of that kind of changes the meaning of the sign, and specifically in this case, the way that a car accident happened. And classifier predicates are never going to exist in data. Very, very rarely are we going to use the same classifier predicate multiple times, because it's a predicate. It's sort of representing a whole sentence. And so using a sign-based approach is not going to get you very far. It's not going to recognize any of the signs, or there aren't signs in it to begin with. And so I think that's a good example of where this sort of, as you said, like an orthogonal approach is going to be 100% necessary here. In this case, like what does a particular movement mean? Well, we can look at other examples of that movement and maybe pick out certain trends that exist.
It's almost like a tone of voice or something like that, or emphasis in local kind of approach. Parallel here.
Yeah. Yeah, and that the idea of tone also applies to facial expressions as well. Yeah. I saw one more question in the back, maybe the last one.
Yeah.
We
so
actually-
correct me if I'm wrong.
We do have another Zoom question that has had their hand up for a really long time. So I want to make sure we get to Ron's question. If that's okay.
I'm interested. Okay, we'll do the Zoom after this one.
Yeah, correct me if I'm wrong. If I said like the vector quantization is kind of like a 2D representation. Do you have like problems like depth? For example, like you see like a palm of the hand that even rotates, still like the same scan, but like different phonological feature.
Yeah. Oh yeah, you're getting at an issue that is sort of in the pose estimation model, which I don't exclusively work on. I feel like I'm more aligned with NLP than vision, but yeah, these pose estimation models are not meant for sign language. And so there's, for example, the hands occlude one another, or like you said, there's depth, like it doesn't really understand depth that well, especially if you're just using sort of like a one camera. And so, yeah, these are important factors that are just going to be really difficult to pick out in the video. Thankfully, frequently, they're not completely necessary to recognize. When it comes to the past tense versus the future tense, the depth does make a difference. For example, like future versus past, they look kind of similar, except future is going forward and past is going behind. Yeah, and then let's do the Zoom question as well.
Okay, so one of the things that has always baffled me about sign languages and ASL in particular is that despite the fact that it's a fairly large, it has a long history, a fairly, in a developed world, it's still an unwritten language. And it doesn't seem like it's developing a writing system. And I know that for example, for speech recognition and stuff like that, you know that the written form of the language loses a lot, but it's still extremely useful, which is why all of us use written language. So my question is, in the work of ASL, do you feel the need for a written form of the language, or do you feel like there's some, you're kind of like developed substitutes for a written form or anything like that?
Yeah, that's a great question. I think virtually all deaf communities do not have a standard writing system, as you point out. In the research, I think that there is a strong argument to be made that we should have something that functions like an orthography or like a writing system. Whether deaf people actually use it is beside the point. What we kind of want is a discrete representation of signing that we can basically treat like characters. I think that's a really strong, convincing argument. I'm not the only person to make this suggestion. Amit Moryasev at UTH Zurich also does most of his work is on sign writing transcription. So this is, instead of thinking of phonemes as these sort of like abstract objects, he has specific like small pictures or iconography that sort of represent each of those as well. And you're able to just visually show the writing itself. I don't know if we need to actually show the writing. I think it's useful as just like, just a computational representation, but yeah, why we don't have writing systems is a complicated cultural question that I couldn't begin to answer. Yeah.
Mashti had a super interesting question at the very beginning regarding dialects.
Oh yeah.
So I wonder whether the structure of dialect groups is maybe quite different from the hearing world.
Yeah.
That's question part one. And then two is, how do the differences really impact the difficulty of the work?
Yeah, absolutely. This is work that I would love to do once I get a assistant professor job. I am on the job market. Yeah, collecting that data is sort of a task unto itself. But in terms of describing these differences in signing styles, yeah, I'm from Memphis in sort of the southern United States, and I've noticed many differences in the way that people sign. For example, the size of the signing space tends to be a little bit larger. I tend to see the sign for no, the hand will be dropped down a little bit. There's a difference between like cop, as in like someone that complains, but it's sort of a variation of cop where the sort of showing the badge. So there are these sort of like,
So the dialects are more geographical then, or?
3 at a time.
Yeah.
Okay. I'll talk to you after.
So just so you know, I think Lee still has time in his schedule. So if you're around,
Yep.
you could probably grab a speaking spot, which I very much encourage you to do.
Sure. Yes, I can talk about this for hours, and there's a really interesting sort of background to how these dialects form. But anyway,
Okay.
Yep.
So
Thank you.
Lee, thank you very much. Thank you to everybody who attended today. Stay tuned for more NLP seminars at ISI. Hopefully there'll be a link to subscribe in the show, in the video notes. Now that I've said it, please make it so. And enjoy the rest of your day. Thanks, everybody.
Yep. Thank you.